Today we're going to review the key ideas from Chapter 7, which was all about similar polygons. So one key concept was knowing how to check whether two different shapes are similar to each other. Remember, similar really just means that they're the same shape, just different sizes. The way that you can check that two figures are similar is you could first check that all the angles that correspond with each other are equal. In other words, you've got a pair of matching angles here, a pair of matching angles here, and a pair of matching angles here. And you could tell by the matching congruency marks. If all the angles pair up and are equal to an angle that corresponds to it in the second shape, that's step one for checking that your triangles are similar. Step two, after you check the angles, is to check the sides. Now, when you're proving triangles are just similar, same shape but different sizes, you don't really expect sides to be equal to each other. Instead, you want them to be proportional. What that means is that when you pair up sides that correspond with each other, it creates a true proportion. For example, if I find the smallest side in both triangles here, and I make a ratio out of that, it should get me the same scale factor that I get from pairing up any other two corresponding sides. So let's pair up the corresponding sides. The smallest two go together, so choose a way to mark them corresponding. Maybe use circles, or maybe you just highlight them in the same color. And then find the largest two sides. Find a symbol to mark those two sides as a pair of corresponding ones. And then the medium two sides. So if we make our ratios of corresponding sides, in other words, if we make our scale factor, traditionally, people often do second shape over first shape, but honestly, if you put the same thing upside down, it's fine. So for the smaller two sides, that's 10 over 8. For the medium two sides, that'd be 15 over 12. For the largest two sides, it'd be 16 over, or 20 over 16, if we're consistently doing second shape over first shape. So we need to see if the ratios of corresponding sides really simplify to be the same scale factor. Both 10 and 8 divide by 2. 15 and 12 divide by 3, 20 and 16 divide by 4, and when we simplify each one, oh, they get us the same fraction, 5 over 4. Because they get us the same scale factor, we can confirm that yes, the sides are proportional and therefore the triangles are similar. Now, this is the method you'd have to use for every shape that has more sides than a triangle. However, if you have a pair of triangles that you're checking for similarity, you have a bit of a shortcut list. These three theorems are shortcuts for proving triangles similar to each other. The AA similarity postulate, remember the squiggly is your symbol for similarity, tells you if you have two pairs of matching angles, that's enough to prove your triangles are similar. Remember, squiggly stands for similarity. Or if you have three pairs of corresponding of sides that make the same ratio like what we did in the last problem, then you could skip checking the angles and say the triangles are similar. Or you could use the SAS similarity postulate. If you have two pairs of sides that make the same scale factor, and you have one pair of congruent angles between them, so it creates kind of a side angle side pattern, that's also enough to skip checking the other angles or the last pair of sides. That would be enough to say your triangles are similar. So this is kind of a useful cheat sheet listing the postulates you could use when you get to the practice problems. There's three other theorems from Chapter 7 that are particularly important. And they all are really providing ways to set up a proportion that you can cross multiply to solve for a missing piece of your diagram. And the rules are based off of the logic of similarity, the idea that the small triangle here is similar to the large triangle it's part of. Anyway, here's the rules. The side splitter theorem says if you have a triangle that's split by a parallel segment to the third side, that's actually splitting these sides in such a way that they're proportional. In other words, I could say x over 5 equals 6 over 7. Oh, I actually get the same thing with the corollary to the side splitter theorem. The corollary to the side splitter theorem says if I make a proportion of sections between three parallel lines, I can use that to solve the problem. X over 5 equals 6 over 7. Yeah, same equation. The triangle angle bisector theorem is essentially saying the same thing as well. If I have an angle bisector, inside a triangle, it's going to split the base in such a way that they're proportional numbers to the sides above the base. So I could say x over 5 equals 6 over 7. So these are really all different ways of setting up a proportion that you could use to solve for x, depending on how the diagram looks. Make sure you fill in this part on your paper. The last thing to talk about is what to do when you already are told you have similar figures and you are asked to solve for a missing side. To start off with, your process is actually going to look quite like our first problem when we were checking to see if the scale factors of corresponding sides matched. So let's pair up sides that go together, that are corresponding in terms of location. So the 6 and 8 look like they go together. The x and 12 look like they should pair up, and the y and the 10.5 look like they should pair up. Notice how the shape kind of got flipped to make the second shape as well as shrunk. So corresponding sides are not necessarily always facing the same direction. You kind of have to see what they look like to see if they're matching parts of the shape. And then you create your list of fractions. You could say 6 over 8 and so on. 6 over 8 equals 10.5 over y equals x over 12. Now when you make your list of fractions, it's really important that you are consistent in terms of putting second shape over first shape. If you decide for the first fraction to put second shape number over first shape number, you have to match that order with the others and keep putting second shape number over first shape number. If I flip this upside down and have first shape over second shape, later when I solve I'll get the wrong answer, so watch out for that. Now that I have my list of corresponding sides put into fractions, I can really just use that to create a proportion that I could solve by cross multiplying. So for example, I can just take the first two fractions here, and I could say, well, that's telling me that 10.5 over y equals 6 over 8, and I can cross multiply to solve for y. I can then essentially do the same thing to solve for x. I could take the fraction that x is in and set it equal to the one fraction that had no variables in it, the 6 over 8, and then cross multiply to solve. And that's it for the notes page. Good luck on the rest of the packet.